In just 10 hours of pointing at the sky, a new telescope found more asteroids than most of the world's observatories combined managed to find in several weeks. Not a typo. 10 hours. Thousands of space rocks nobody had ever seen before. Several of them close enough to Earth to actually matter. And that was just the warm-up. Stick around because what this telescope has done since then is even stranger. And if you want to keep up with every discovery it makes going forward, hit follow right now before we get into it. The telescope responsible for this is called the Vera C, Rubin Observatory, and it officially opened its eyes to the public on June 23, 2025. It sits high on a mountain called Cerro Pachchon in Chile, in the middle of the Atacama region, one of the driest, darkest, and most consistently clear patches of sky anywhere on the planet. That location was not chosen by accident. Almost no rainfall, almost no light pollution, and remarkably stable air that does not distort incoming starlight nearly as much as most other places on Earth. It is exactly the kind of environment astronomers dream about when they are trying to squeeze every last drop of clarity out of a ground-based instrument. For most of the last few decades, the dominant assumption in astronomy has been that if you truly want the sharpest possible view of the universe, you have to leave Earth's atmosphere behind entirely, which is exactly why observatories like Hubble and the James Webb Space Telescope were launched into orbit or beyond in the first place. Ground-based telescopes have always had to fight against atmospheric blur, shifting temperature layers, humidity, and even faint distortions invisible to the naked eye, but very obvious to a sensitive enough camera. The Atacama Desert largely sidesteps that problem simply through geography. The combination of extreme altitude, bone-dry air, and a location far from any major city's light pollution creates one of the most stable, transparent air columns anywhere on the surface of the planet, which is part of why the same general region already hosts a number of the world's most important telescopes. Building here let engineers pair an already exceptional natural setting with a three-mirror optical design, an automated nightly scanning system that together minimize the remaining atmospheric limitations most other ground observatories still have to contend with. Here is what makes this observatory different from basically everything that came before it. Most telescopes are built to zoom in. They pick one small patch of sky, a single galaxy, a single star cluster, and they stare at it with incredible precision, gathering as much fine detail as possible from a very narrow slice of the universe. The Rubin Observatory does almost the opposite. Its entire design exists to capture huge swaths of sky in a single shot, then repeat that process over and over again, night after night, for 10 straight years, building something closer to a time-lapse movie of the entire visible universe rather than a photo album of individual objects. At the heart of this machine sits the Simony Survey telescope built around an 8.4-meter primary mirror, using a three-mirror design that is unusual even by observatory standards. Behind that optical system sits the actual camera. And this is where things get genuinely absurd in scale. It is the largest digital camera ever constructed for astronomy. Roughly the size of a small car, weighing close to 3 tons and capturing images at 3.2 billion pixels per shot. For comparison, most phone cameras today shoot somewhere around 12 to 50 million pixels. This camera captures more than 60 times that in a single exposure. One picture from this telescope covers a patch of sky wide enough to fit roughly 40 full moons side by side. To get an equivalent amount of coverage, a telescope like Hubble would need to take thousands of separate images and stitch them together piece by piece. The engineering behind that camera deserves a moment of its own attention, because it is not simply a bigger version of a normal camera sensor. Inside sits an array of nearly 190 individual sensors, each one carefully calibrated, so that when the images are stitched together, the seams between them essentially disappear, producing one seamless picture rather than a visible patchwork. In front of those sensors sit 3 enormous lenses made of fused silica precision ground glass, one of which holds the distinction of being the largest lens ever manufactured specifically for astronomical use. Together, these lenses correct for distortion across the camera's unusually wide field of view, which matters enormously for a survey telescope. Without that correction, a star sitting near the edge of the frame would appear smeared or warped compared to one sitting in the center, which would badly undermine the precision this kind of large-scale survey depends on. The camera can also swap between different optical filters using a robotic mechanism, letting it capture ultraviolet, visible, and near-infrared light in quick succession. Each wavelength range revealing different physical properties of whatever it happens to be looking at, from the temperature of a distant star to the chemical composition of a gas cloud. This is not really a camera in the traditional photography sense at all. It behaves more like a multi-layered scientific instrument, where every single exposure carries hidden information beyond just a pretty picture. Subtle chemical signatures, thermal patterns, distortions caused by gravity bending light from objects behind other objects. Even the faint trails left behind by things that move during the exposure itself. Extracting all of that hidden structure from each image is really the entire point of the exercise, far beyond simply producing something visually impressive to look at. If a fact like that already has your attention, imagine what happens when this telescope actually starts working through its full 10-year survey. Go ahead and subscribe now if you haven't, because the numbers only get more ridiculous from here. When the observatory finally revealed its first test images to the public in June of 2025, the scientific community had been anticipating the moment for years. And even so, what came back exceeded most expectations. Engineers and astronomers had run just over 10 hours of test observations, a tiny fraction of what the telescope would eventually spend looking at the sky across its full mission. And in that short window alone, it produced a mosaic that quickly earned the nickname, the Cosmic Treasure Chest. This particular image focused on the southern region of the Virgo cluster, the nearest large collection of galaxies to our own Milky Way. And it was built by combining roughly 1,000 individual exposures into one seamless picture. Inside that single mosaic sat millions of stars and galaxies, spiral galaxies with arms stretched lazily across space. Pairs of galaxies caught mid-collision, faint threads connecting distant clusters like a cosmic spiderweb. And here's the part that puts the scale of this entire project into perspective. That entire breathtaking mosaic represented roughly 1/120th of 1% of what the observatory is expected to eventually capture over its full mission. In other words, that jaw-dropping first image was closer to a trailer than the actual film. The observatory also released a wide-field mosaic, capturing two well-known star-forming regions, the Triad Nebula and the Lagoon Nebula, both several thousand light-years away. Built by combining more than 600 separate exposures taken across roughly 7 hours of observing time. Normally, when people see images of these nebulae, they come from telescopes designed to zoom tightly into the glowing clouds of gas and dust themselves, filling the entire frame with just that one structure. The Rubin Observatory did something different. Because its field of view is so enormous, the nebula appeared as just one part of a much larger neighborhood surrounded by open star clusters. Dense globular clusters packed with ancient stars and countless other points of light that would normally require an entirely separate observation to capture. It was less like looking through a keyhole at one room, and more like having an entire house's floor plan revealed all at once. This single image also perfectly illustrates why this telescope's approach genuinely does something new. Hubble, one of the most celebrated telescopes ever built, captures roughly 1% of the Moon's surface area in a single image when it's zoomed in on a target. This new observatory captures an area equivalent to about 40 full moons in one shot, while still keeping enough detail that a star sitting at the very edge of the frame looks just as sharp as one sitting dead center. These two approaches to astronomy are not really in competition with each other. One is built like a microscope, perfect for studying the fine anatomy of a single object in extraordinary detail. The other is built more like a wide aerial survey, revealing how that same object fits into the broader structure surrounding it. Used together, they genuinely complement each other in a way that neither one could achieve alone. If understanding how these tools work together is the kind of thing you find genuinely interesting, make sure you're following because we're just getting to the part where this telescope started breaking records for actual scientific discoveries, not just pretty pictures. Beyond the visuals, the real headline coming out of that first 10-hour test run was what the observatory found moving through our own solar system. In that short window, it identified more than 2,000 new asteroids, a number that included several classified as near-Earth objects, meaning their orbits bring them close enough to our planet that tracking them matters for planetary defense. To put that number in perspective, all of the world's combined asteroid tracking observatories, working together throughout an entire year, typically identifies somewhere around 20,000 new asteroids total. This one telescope matched a meaningful fraction of that entire annual total in less than half a day of test observations before its full survey had even officially begun. And this observatory did not stop there. As its commissioning phase continued through the following months, scientists kept combing through the growing pile of data, and the discoveries kept multiplying. Researchers eventually confirmed just over 2,100 new asteroid discoveries from that initial commissioning window alone, drawn from roughly 340,000 individual detections collected across about 9 nights of observing between late April and early May of 2025. Buried inside that data set was something genuinely remarkable. Astronomers identified an asteroid now cataloged as 2025 MN45, measuring roughly 710 meters across, wider than 7 football fields laid end to end. What made this particular rock stand out was not just its size, but its spin. This asteroid completes a full rotation once every 1 minute and 53 seconds, making it the fastest spinning asteroid of its size ever recorded. Scientists studying it noted that for a solid object that large to spin that quickly without simply flying apart, it would need to be made of remarkably strong, cohesive material, essentially holding itself together against forces that would tear apart a loosely packed pile of rubble. That single discovery, found almost by accident while astronomers were still testing the telescope's capabilities, gave researchers a genuinely new data point about how these ancient objects are actually built. As the observatory moved further into full operation, the pace of discovery only accelerated. In a more recent survey period spanning roughly 6 weeks, the telescope logged around 1 million individual observations, resulting in the identification of about 11,000 brand new asteroids alongside repeat observations of roughly 80,000 previously known ones. Some of these newly identified objects pass close enough to Earth's orbit to be worth tracking carefully going forward. Taken together, these results suggest that over its full planned mission, this single observatory could end up discovering millions of asteroids, comets, and other small solar system bodies, fundamentally reshaping how completely we understand the population of objects sharing our corner of the solar system. There's a genuinely important practical reason this matters beyond scientific curiosity. Planetary defense. The effort to identify potentially hazardous asteroids long before they could ever pose a real threat to Earth depends entirely on actually knowing these objects exist in the first place. A telescope capable of scanning huge portions of the sky repeatedly, catching faint, fast-moving objects that previous survey efforts would have simply missed, gives scientists dramatically more lead time to study any concerning object's orbit and rule out or confirm any potential future risk. This observatory is quickly becoming one of the single most important tools humanity has ever built for that exact purpose. If you appreciate a channel that explains why a discovery actually matters instead of just repeating a flashy headline, go ahead and hit that subscribe button now because there's still a lot more this telescope is built to do. And some of it is even stranger than hunting asteroids. Finding thousands of asteroids was really just a side effect of testing the equipment. The observatory's actual 10-year mission is built around 4 major scientific goals: and asteroid hunting is really only a fraction of one of them. The second major goal focuses on something this observatory is uniquely suited for: catching transient events, meaning anything in the sky that changes, flares up, or disappears on a timescale ranging from minutes to a few days. Because the telescope is designed to scan large portions of the sky roughly every few nights rather than staring fixedly at one target, it functions almost like a security camera pointed at the entire universe at once. Supernova exploding in distant galaxies, gamma-ray bursts, sudden stellar flares, and other short-lived cosmic events that earlier telescopes would often catch only after the fact, already fading, can instead be caught right as they're happening, giving scientists a genuine head start on studying them while they're still active. Before this kind of rapid repeating survey existed, catching one of these brief cosmic events required a fair amount of luck. A supernova might ignite and begin fading before any telescope happened to be pointed at that particular patch of sky, meaning astronomers would only catch the tail end of the event, missing the crucial early stages entirely. By scanning enormous portions of the sky every few nights and comparing each new image against everything captured before it, this observatory can flag the instant something changes, brightens, dims, or appears where nothing was previously visible. That shift transforms astronomy from something closer to occasional spot checking into something closer to continuous monitoring, catching stellar deaths, violent collisions, and other short-lived phenomena in the earliest moments of their existence rather than stumbling across the aftermath. Each one of these caught in progress gives researchers a far more complete picture of the actual physics driving these events, information that is often lost entirely once an event has already faded past its peak. The third goal involves mapping the structure of our own Milky Way galaxy in far greater detail than has ever been possible before, largely using a specific category of star called RRLIY variables. These are ancient stars that pulse in brightness on a predictable, well-understood cycle, which makes them incredibly useful as what astronomers call standard candles, essentially cosmic mile markers that let scientists calculate precise distances across the galaxy. During its very first test observations, the observatory had already identified several dozen of these pulsing stars, and researchers expect that number to eventually grow into the hundreds of thousands across the full survey. Many of these stars sit out in the faint, sparsely populated outer regions of our galaxy, in areas that have historically been extremely difficult to study, simply because the stars there are so dim and spread so far apart. By tracking huge numbers of them, scientists hope to trace out faint stellar streams left behind by smaller galaxies that collided with the Milky Way in the ancient past, essentially reading the scars of our galaxy's violent early history written into the positions of these ancient stars. It's worth explaining briefly why standard candles like these matter so much to astronomers in the first place. Measuring distances in space is genuinely one of the hardest problems in the entire field, because unlike measuring distance on Earth, you cannot simply stretch a tape measure between 2 points floating in the void. Instead, astronomers rely on objects whose true brightness is already well understood through decades of prior study. Then compare that known brightness to how dim the object actually appears from Earth. The dimmer it looks compared to its known true brightness, the farther away it must be. Our library stars are especially useful for this because their pulsing cycle is so consistent and well characterized that astronomers can identify them with confidence and immediately calculate a reliable distance. Multiply that single measurement across tens of thousands, and eventually hundreds of thousands of these stars scattered throughout the galaxy's outer halo, and you end up with something close to a full three-dimensional skeleton of the Milky Way's true shape, including faint structures that were essentially invisible to earlier generations of telescopes simply because nobody had enough of these markers to connect the dots. The fourth goal is simply to create the most complete and detailed catalog of solar system objects ever assembled, which brings us right back to where we started. All of those asteroids along with comets and potentially something even rarer. Every so often, an object passes through our solar system that did not originate here at all. something that formed around an entirely different star, got flung out into interstellar space, and happens to drift close enough to our Sun for us to notice it before it continues on its way, never to return. Scientists have only confirmed a small handful of these interstellar visitors in all of recorded history, and each one was discovered somewhat by luck, spotted only days or weeks before it became too faint to study properly. Because this new observatory scanned such enormous portions of sky on such a rapid repeating schedule, it is expected to dramatically improve our odds of catching these rare visitors early, potentially, while they are still far enough away to give scientists months of advance notice instead of just days. Researchers studying interstellar objects are genuinely hopeful that over its 10-year mission, this observatory could detect several more of these ancient travelers, each one carrying frozen chemical fingerprints from a completely different star system, offering scientists a genuine sample of material that formed somewhere else in the galaxy entirely. The reason earlier interstellar discoveries were caught so late really comes down to exactly the limitation this observatory was built to solve. Older survey telescopes typically covered much smaller patches of sky per exposure and revisited any given patch far less frequently, which meant a fast-moving, faint object drifting through on a steep, unusual trajectory could easily slip through the gaps between observations for weeks before anyone noticed a pattern. A telescope covering huge swaths of sky every few nights dramatically shrinks those gaps. Something moving unusually fast on a path that doesn't match anything gravitationally bound to our Sun is far more likely to get flagged early, while there's still enough time left before it fades from view to actually point other major telescopes at it, gather detailed spectra, and study its composition properly instead of scrambling to catch a fading, disappearing target. Stepping back to the first of those four goals, the most ambitious one involves mapping dark matter and dark energy, two of the biggest unsolved mysteries in modern physics, by tracking how billions of galaxies are distributed and how they move relative to each other across vast stretches of cosmic time. Scientists cannot see dark matter or dark energy directly, but by measuring how galaxies cluster together and how that clustering pattern subtly bends and distorts light from objects behind them, researchers can begin piecing together indirect evidence about what these mysterious forces actually are and how they behave. To understand why this specific telescope is so well suited to that particular challenge, it helps to know that both dark matter and dark energy reveal themselves only through extremely subtle statistical patterns spread across enormous numbers of galaxies, not through any single dramatic observation. A telescope that can only study one galaxy at a time, no matter how sharply, simply cannot detect these patterns because the signal only becomes visible once you have measured the shapes, positions, and distances of tens of millions or ideally billions of galaxies spread across huge stretches of the sky. That is precisely the kind of task this observatory was purpose-built for. Its combination of an enormous field of view and repeated scanning over a full decade means it will eventually build up a catalog of galaxy positions and shapes on a scale that was simply never possible before, giving physicists their best opportunity yet to measure exactly how these invisible forces have shaped the structure of the universe over billions of years. Now, all of this scientific ambition creates an absolutely staggering data problem. And honestly, solving that problem might be just as impressive an achievement as building the telescope itself. On a normal night of observing, the observatory generates around 20 terabytes of raw data, an amount that would overwhelm most traditional data systems almost immediately. To handle it, engineers built a dedicated high-speed fiber connection specifically to beam that data from the mountaintop in Chile directly to processing centers in the United States, where automated systems immediately begin calibrating images, correcting for atmospheric distortion, identifying anything that moved between exposures, and flagging anything that changed brightness unexpectedly, all before a single human scientist has even looked at the results. Over the full 10-year survey, the observatory is expected to accumulate somewhere in the neighborhood of 500 petabytes of data, an amount so large that fully analyzing it will likely take research teams years, if not decades, working long after the observing mission itself has ended. What makes this even more remarkable is that a significant portion of this enormous data set will actually be made accessible to the public, not just professional astronomers with access to specialized supercomputing facilities. Tools have been built specifically to let ordinary people explore these massive high-resolution images directly, zooming from a wide view containing millions of galaxies all the way down to individual stars and structures. The same way you might zoom around an online map, this effectively opens the door for citizen scientists and curious members of the public to potentially spot something genuinely new themselves. Whether that's an overlooked supernova, an unusual asteroid, or some faint object that automated systems initially missed. Given how much data this telescope produces every single night, having more curious eyes looking through it is a genuine advantage, not just a nice educational gesture. This kind of public access also represents a fairly significant shift in how large scientific projects tend to operate. For a long time, working with genuinely cutting-edge astronomical data required institutional access, specialized training, and computing resources most individuals simply did not have. By deliberately designing public F-facing tools around a data set this enormous from the very beginning, the project effectively lowers that barrier substantially, letting students, hobbyists, and anyone with a genuine curiosity engage directly with frontier-level astronomical data, rather than waiting years for a simplified secondhand summary to eventually trickle down through textbooks or documentaries. Given that professional research teams will likely spend years, if not decades, working through the full dataset, even with automated systems assisting them, that broader participation is not just a nice gesture. It genuinely increases the odds that something unusual buried in the data gets noticed sooner rather than later. Stepping back, it's worth appreciating just how unusual it is for a ground-based observatory to be generating this much scientific excitement in an era so thoroughly dominated by space telescopes. For decades, the assumption in astronomy has generally been that if you want the clearest possible view of the universe, you send your telescope above the atmosphere entirely, the way Hubble and the James Webb Space Telescope both did, specifically to escape the blurring, shifting, light-polluting effects of Earth's own air. This new observatory proves that a sufficiently well-designed, well-positioned, ground-based telescope can still compete directly with that approach, at least for the specific kind of wide-field, rapid repeated scanning this project was built around. It does not replace space telescopes, and it was never meant to. Space telescopes remain unmatched for zooming deep into individual targets with extraordinary precision. But for serving enormous stretches of sky quickly and repeatedly, watching for change rather than studying one fixed target, this ground-based approach turns out to be extraordinarily well-suited to the job and remarkably cost-effective compared to launching an equivalent instrument into orbit. So, here's what all of this really adds up to. In a single 10-hour test run back in 2025, before its real mission had even officially started, this observatory produced a mosaic containing millions of galaxies, revealed the hidden neighborhoods surrounding two famous nebula, and discovered more new asteroids than most observatories manage in weeks of dedicated searching. In the time since, it has kept adding to that total, uncovering objects like the fastest known spinning asteroid of its size, and logging thousands more newly discovered space rocks with every additional survey period. And this is still just the opening act. Over the coming decade, this single instrument is expected to map the structure of our own galaxy in unprecedented detail, hunt for signs of dark matter and dark energy across billions of galaxies, catch cosmic explosions and flares in the exact moment they happen rather than after the fact, and give humanity its best chance yet at catching rare visitors passing through from other star systems entirely.